Hello everyone, we're in the middle of the proof of the spectral radius formula, which is still shown here on the slide. So if you are working in a complex Banach space and you have a bounded linear operator on it, then you can compute in a sense, the largest eigenvalue in the spectrum for this formula here. The limit as n goes to infinity of the nth root of the operator norm of the nth power of t. This will be our goal now to prove, once we have it, that second statement here about complex Hilbert spaces and normal operators is actually quite simple to figure out. All right, so we started with some algebra, and that is this here with the yellow star. And now the following message. So if you start with something in the spectrum of t, then either, well, kernel lambda I minus t is non-trivial, because then the guy is not injective, or the range is not everything. The guy is not surjective, all right, since you're on the spectrum. Now I claim from this, maybe I should write hence. Hence, lambda n is in the spectrum of the nth power. And why is this? Well, this is because of the yellow star. Right, so let's do proof by contradiction. If lambda n were in the resolvent, right? If lambda n were in the resolvent, that means lambda n both injective and surjective, right? So let's play around with surjective. Surjectivity means for all y in x there exists x in x, so that y is lambda n I minus t to the nx, right? Because surjectivity, and now you use the yellow star. In particular, you can use the first equation. Maybe let's use a color here. So first equation, then you would have lambda I, oh, not blue, but yellow. Lambda I minus t. And then this blue bracket here I will write as rest, and then times x, right? Yeah, but now I have a statement here that says for all y in x there exists a modified element, which is rest times x, such that lambda I minus t times that pink stuff is equal to y. Yeah, but that would mean that lambda I minus t is surjective, which contradicts that I'm in the spectrum. So it's either non-injective or not surjective. It's or, it doesn't mean and, right? So that leads to a contradiction. And now you do the same thing with injectivity. So injectivity, if this thing were injective, then how can you say, then this means lambda n I minus t n x equal to 0 if and only if x is equal to 0, right? This is injectivity. From the right to the left, this is just linearity, but from left to right, that is injectivity, right? So you have this equivalence, right? But since you on the spectrum of t, there exists non-zero, maybe one can't see this right, so let's write it on the next page. Injectivity. So injectivity would mean lambda ni minus tn times x. 0 happens precisely when x is equal to 0. But there exists an x naught which is non-zero, so that lambda I minus t x naught is equal to 0, right? Because lambda is in the spectrum of t, right? So there exists non-trivial solution to the homogeneous equation there, right? So, but once you have this, then of course, since lambda n I minus t n x naught, you can use the second equation here. Let's do it like this. Use the second equation. And then you have sort of rest here to the left, and then lambda I minus t x naught, right? But whatever is there to the left doesn't really matter, because already this is, it matters that it's linear, that of course matters, because this is already 0. That's precisely what's written here. So this is mapped to 0, right? So in other words, you have here now a non-zero solution to lambda n I minus Tn x naught is equal to 0, and that contradicts what's written up there. Right? So either way, it is a contradiction, and hence that claim here that if you have lambda in the spectrum of t, that then the nth power has to be in the spectrum of t to the nth power, that is a true statement. Okay, good. So having this, now what we do, hence, let's start with rt to the power n. Okay, so rt by definition is that supremum, which is a non-negative number. Could be 0, but certainly not going to be negative infinity, because I'm over a complex Banach space. So this to the power n, then here is easy rule of evaluating suprema of real numbers. The power goes in. But now what I just showed was lambda sigma t implies lambda n in sigma Tn, right? That's the implication that I showed. Yeah, but that translates immediately to an inequality here, namely if I run the supremum over lambda n in sigma Tn instead of lambda over sigma t, right? Then you will have an upper bound because of this red implication. Okay, but now here on this right hand side you could just relabel lambda n sort of equal to mu. Then you would have here supremum mu in sigma Tn of mu, because the complex modulus and that nth power, you can swap the order. And this is precisely by definition the spectral radius of the nth power of t. Okay, so you got this inequality between the nth power of the spectral radius of t and the spectral radius of the nth power of t. All right. However, we already know some more. We know that the spectrum is sitting in a disk of radius at most equal to the operator norm t. So what we get from this guy up there is r t. What do I mean by this guy up there? I mean, okay, this one is at most, so nth root of r Tn. This is precisely the yellow one. And now you apply, well, this equation up here, this inclusion here, is not with t, but with t to the power n, right? So then you obtain from this one at most n t to the power n, right? That's what you have by green star. Okay, so and this is valid for all natural numbers. Okay, consequently you can take limits, and we were gonna be taking the limit inferior, n goes to infinity, n t to the power n. And just if you don't remember what lim_inf is, well, as the limit as n goes to infinity over all these infima. So k, at least n, and then k t k. Okay, that I can do. All right, good. So now the next task will be to show a reversed inequality where the lim_inf or the infimum here is replaced by a supremum, and then you will have sort of a squeeze argument that will give you the actual equality for the spectral radius, aka the spectral radius formula. So we now show that lim_sup n goes to infinity, nth root of operator norm of t to the n. So here's definition, in case it's not known. So the inf is replaced by sup kn k t to the k, that this cannot exceed the spectral radius. All right, and then you will have a nice squeeze argument, then there's just equality in the middle. Good. So how to do this? Now this will use now two inputs. It will use complex analysis and it will use the principle of uniform boundedness. Right? So a nice combination of arguments. Well, at least if you're familiar with complex analysis. Okay. We now show that and recall to this end the following expansion that we already used in the proof that the spectrum is non-empty. If you have a complex Banach space, there was this following, I called it Laurent series representation of the resolvent, well, Neumann series in negative powers of lambda, identity plus n1 this, tn lambda to the minus n, and this just, I write it in one series with one summation. Sigma is just this one here. You can easily check. Just rewriting this, all right? So that the Laurent series, and this series converges for lambda in that domain outside that disk with radius operator norm of t. And this means in turn so that the Laurent series, so now we are back in complex analysis, the Laurent series h of lambda, which is n0 infinity f tnx lambda minus n minus 1 for lambda at least t. And remember, when I started discussing this spectral radius formula, I said in application it's only useful when you have some symmetries, because you can easily get a trivial estimate from the spectral radius formula, and this was precisely this one, that the spectral radius cannot exceed the operator norm, which we already know, right? So that's what I just wrote here, okay? So that this Laurent series converges in the indicated domain for lambda for all linear functionals, continuous linear functionals, and vectors x in x. Okay, good. Hence, by the necessary convergence criterion for series, this is a series here in the complex plane, this h of lambda, right? This takes values in the complex plane. Input value is the lambda, output value is some function in lambda, right? We fix that x and the linear functional, right? So converges for all linear functionals and vectors x. Hence, the sequence, well, lambda minus n t n x, n from 1 to infinity in x, must converge weakly. This is the necessary criterion for convergence, right? The necessary criterion says that everything here that involves the n, so this piece here as n goes to infinity has to go to 0, and since this holds true here for all a continuous linear functional, that precisely saying that this sequence here converges weakly, okay, to 0, must converge weakly to 0 for all vectors x, okay? But weakly convergent sequences are bounded. This was already an application of principle of uniform boundedness. But weakly convergent sequences are bounded. So, for all vectors x, the following supremum, lambda minus n t to the nx and n ranging through all natural numbers is finite. All right, and now you should realize what I'm doing here. So I've now just defined a family of objects that is pointwise bounded, which says that this family f, which is lambda to the minus n tn, so that's a family of bounded linear operators indexed by n, is pointwise bounded. Right, since we are working over a Banach space, this is a T maps x to x, x is a Banach space, the principle of uniform boundedness says, hence by pub we have uniform boundedness of the family. So supremum lambda minus n Tn n in n is finite. Okay, so what does this mean? There exists C positive, so that, well, all these lambda minus n t to the n in operator norm cannot exceed that constant C. If you bring the lambdas to the other side, this just says this one here, okay, for all natural numbers. And now we're done. Thus, if you look at that lim sup n to infinity, there was the nth root of t to the n in operator norm. Now you use this one here. Maybe first you don't take the limit, just work for arbitrary n and then push n to infinity. And then you have what? So there will be certainly lambda, because lambda comes to the power n here, and I take an nth root, so that gives me a lambda. And then you would have the nth root of this constant c, and c is independent of n. That's the important thing, okay? That's what we got from the pub. But then if you take the nth root of any positive number as n goes to infinity, that converges to 1, right? So you have this, what I just wrote, okay? And of course, lambda does not exceed in complex modulus the largest lambda in the spectrum, so that is clearly bounded by the spectral radius. All right, altogether, if we combine the first part where we had that statement with the lim inf, that was this guy, n infinity n tn. Now the lim inf, as you could imagine, is bounded above by the lim sup, and then this, and now I just showed that that lim sup is bounded by the spectral radius, and there you have it. So that's the double inequality, okay, which gives the desired identity, right? Because this double inequality tells me that equality appears everywhere, and then the lim inf and the lim sup have to be the same, and hence they are the limit. Okay, good. Which gives the desired identity. Now what remains to be shown is that if you have normality in place, then you can actually get rid of all these n's. So if you're now on a Hilbert space is normal, then tx, okay, I claim that the operator, the norm in the Hilbert space of tx and the adjoint acting on x is the same for all x in x. That should be clear. So if you square both sides, yeah, maybe here. So if you square both sides, then you have tx squared. Since you're in a Hilbert space, that's precisely this guy. Then you move this over with the adjoint. And since you are in the normal setting, t is normal, that means you can swap here the order. So you have x, t, t star x, and then you move this guy back and it gets the adjoint on the first guy. Right, and this is precisely the norm squared of t star x. Right, so this is true, okay, for all x. So in particular, well, replace x by t of x, so then you have t squared of x is equal to t star t of x, from which we deduce, well, operator norm of t squared. Remember what this is? This is the supremum. You go with a unit ball with radius 1 of t square x. Here my operator is just t squared instead of t. Then I use, well, this equality. That's not an estimate, that's an equality. Supremum x, x1, t star tx. Yeah, and then by definition of the operator norm, this is the operator norm of t star t. However, when we defined the adjoint, the first result, which is quite long, was a theorem that said that the operator norm of the t adjoint times t is the same as the operator norm of t times t adjoint is the same as the operator norm of t squared. Right, so I use this t squared. Okay, this is from that previous theorem. So you have this, so that means you can just pull out the square. Right. So in turn, if you now iterate this procedure, you can do this with any 2nth power. So t to the 2n is equal to t to the 2n, right? So since we already figured out this limit exists, I can approach infinity in any fashion I want, right? That's the beauty of limits. Once you know that they exist, you can creep up to infinity in any way you want, and I will just do this by running through all 2k powers, right? So 2k roots, t 2 to the k, and now I use what I just had, that once you have this powers of 2, you can take the powers outside here, and now they precisely go out, right? So what remains is indeed t. Okay, and that's it. That's the end of the result. Okay, nice, very nice. Okay, so this is the spectral radius formula. I think it's very nice proof, but of course it requires some complex analysis, that knowledge about the long-run series being convergent somewhere, and then we use the principle of uniform boundedness. Okay, some further results that come in handy, and we actually used them implicitly. This is sometimes called Phillips' lemma. It goes as follows. So let X be a Banach space, and say A bounded linear operator. Then, so you can ask yourself, how is the spectrum related, the spectrum of A related to the spectrum of the dual transformation of A? And is there any relation between the resolvent of the dual transformation and, no, I already give it away, I already wrote the equality, and the resolvent of A? Well, turns out these guys are the same, and this is the same, and the dual goes up there. Okay, so let's move this inward. So we have this, that thing we actually haven't used yet, but we have used the second one. In our example with the right shift, at some point we looked at the dual, namely the left shift. Not the dual, the adjoint, right? So there is a similar relation for the adjoint. If H is a Hilbert space and T bounded linear operator, then the spectrum of the adjoint. Now in that example, really, we didn't really see that because the spectrum was the unit disk, and that is symmetric under complex conjugation. But in general, what is true, the spectrum of the adjoint is just the values, all lambda, such that complex conjugate lambda is in the spectrum, right? So in particular, if you are working over a real Banach space, then the spectra of the adjoint and T are the same, right? Moreover, the resolvent has a similar property, so this resolvent is just the adjoint of the original one. Okay, so that is true. Let's move this here a bit closer. Okay, these things are easy to prove. I will only address that one about the dual transformation. The one about the adjoint should be clear. And this is simply the one with the adjoint. Why is there a complex conjugate bar? Well, because this mapping is not linear, but conjugate linear. Okay? And to prove this formula as well, you have to also use that, of course, if you take the adjoint of the adjoint, you get back to T. Okay? I will not say details. This is clear from the definition, right? So because this formula tells you in particular that T is invertible if and only if the adjoint is invertible, right? And that's why you have this nice relation there. Up here, this is not true. The dual transformation is in general, you can't bring this argument. The dual transformation in general not invertible if and only if the original one is invertible. We have only one direction. That was the one that if A is invertible, then the dual transformation is also invertible. Okay, and that thing, that what I just said, if the dual, if A is invertible, then the dual is invertible. This will tell you that the resolvent of A is a subset of the resolvent of the dual transformation of A. In turn, taking complements, this means that you have the other inclusion for the spectrum, okay? That you have this. Now, how do you get equality up there? Well, so assuming that the spectrum of the dual transformation were a proper subset, look at the spectral radius that we just discussed. So is there a relation between the spectral radius of A and the dual transformation of A? Well, there is one, and it's a hard equality. And this is because this map is an isometry, right? So the operator norm, in other words, of A and the operator norm of the dual transformation of A are the same, right? So if you had here a proper containment, then you would get a contradiction to the spectral radius formula, right? Because then the spectral radius here of the left of the dual of A would be strictly less than the spectral radius of A, and that cannot be because we know that they are equal, right? So indeed you have equality here. This statement up here is easy because instead of having a conjugate linear map, this map is linear. Right? That's why that little t just goes out, and you don't have to change the lambda. Okay, yeah, in the notes I just say this follows immediately from this and that theorem, and here in yellow and green you have some more reasons. Okay. So now we'll stop now. I will just give a look ahead. So we will now do another example using already now various things that we already learned. And then there will be one general theorem that concerns operators on Hilbert spaces that have built-in symmetries. So there's a beautiful fact that actually that is very easy. If you're over Hilbert space and you, for instance, have a normal operator, and then immediately the residual spectrum is empty. Okay, so that part you don't have to concern yourselves about. You just have to find the eigenvalues, the point spectrum, and then well, you have to find the whole spectrum as well, but then the continuous spectrum you get for free as the complement of the eigenvalues, because residual spectrum is empty. Okay, and this we will do in the next video. Okay, I'll see you then.